specifically on page 447, and we're letting dilations show us how we have similar figures. Let's get into this one. I've got a protractor, I've got some tracing paper, highlighter, pencil, pens, etc., the works, because you're going to need them for success on this page specifically in this moment. So be ready, let's go. You're going to dilate figures by a scale factor. And so we want to start this problem by understanding that when you think of y, like the flashlight, it's the center of the dilation, and everything is growing in proportion away or maybe in reverse towards that center. So we're going to say that triangle DEF, that's bigger and this kind of like off-color pink, is a dilation of triangle ABC. Note on the side, a dilation is a transformation that is either going to stretch or shrink the figure, and so those are the two directions. But there has to be a fixed point or center of the dilation. Let's draw that in. Pencil is the best because we want to imagine that we could erase these lines. Start by taking the straight edge of your protractor, lining it up on Y, and then we're going to draw a long, long line from Y through A, through D, off the edge of the paper. And if I had more poster paper, I would continue to draw that. And let's do that for the other vertices of the triangle, Y through BE and Y through CF. Since this arrow that goes through CF and it starts at Y, all of the arrows coming that pass through the sides of matching corners or vertices of the triangle, they all start in the same location. This is the center of the dilation. In this case, for our example, it's going to be Y. Now, we're going to draw the path YD, YE, and YF. And I think I'm going to use a highlighter to do that. So YD is this one. YE is this one. I was a little bit off thanks to my pencil being so sharp and amazing. And YF is the last one. Those paths are coming off from the flashlight, from Y flashlight location. And they're passing through the object. Now, this is the shadow. This is the pre-image, a little bit of contemporary math words. This is the pre-image, and this is the image. Now, use a ruler to determine the actual lengths of YA. So I've set up my paper here for success, and I know that on the inside edge of my protractor, I've got centimeter measurements, and so I'm going to use those. I want to measure the length of YA. And as I line it up, maybe lining it up from A to Y, I'm noticing I got to make sure 0 goes on A, and then I'm going to count, right? And every little spike on this edge is not a full centimeter because it goes by tens. Those are millimeters. So I'm going to go 1, 2, 3, 4, 5, 10, 15. I'm going to say it's about 17 millimeters, and that would be 1.7 centimeters. When you get your millimeter measurement, which is just every single little tally, you divide by 10, which is moving a decimal point over. Do the same thing for YB. YB is starting at B, lining up with Y. It looks like it's about 2 centimeters. So sorry if there's a glare, it's kind of tough to see. 1 centimeter, 2 centimeters, YB. YC is the third side connecting the flashlight center of dilation Y to C, making sure I'm on 0 on 1 point, and then counting out tally marks, I get 15 tally marks, or 1.5 centimeters for this last one. We're going to keep doing that all the way around, YD, YE, and YF. Now, I'm going to go ahead and do that myself and just, kind of stop talking. You should skip forward in the video and see if our measurements are close, are accurate, and then, catch up to where I am, okay? So I'm measuring YD, YE, and YF in millimeters. That looks like it's about 4.12, 4.2. YD, 4.2 centimeters. YE, 5.1 centimeters. And then YF, a little under, maybe 3.8 centimeters. Okay, I've got my calculator on my phone ready to go. That number was from something totally unrelated. Okay, so we want to take those measurements and make ratios of them, because when we talk about similar figures, the math isn't to say like, look, I have a measurement and it's this long of a measurement. The math is actually to say, well, let's make a fraction from those measurements from one triangle of the pre-image to the other triangle of the image. And notice it's image over pre-image measurements. Maybe that's a note on the side. Image over pre-image. That's how we're going to determine scale factor then, right? So the image measurement goes on top, the pre-image measurement goes on the bottom. And if I have my list already made up right here, YD is 42 or 4.2 centimeters, and YA is 1.7 centimeters. So then I go 4.2 divided by 1.7, and I get approximately 2.47. I'm going to say that's a scale factor, but I should also confirm it. We should have the same measurements for scale factor numbers if we've accurately done the problem. So now I'm going to find YE. I notice that that's 5. And YB, which is 2. And let's just check. What is 5.1 divided by 2? 2.55. I'm off by a little bit. Mostly out of accuracy. We're in the ballpark, and I'll say this is just my rounding error. We're in the ballpark of 2.5. And I will totally blame the tool, or I will blame myself about whether or not we're accurate or not. Let's keep going. Number 3. Use a protractor to measure the corresponding angles in the triangles. And I've got my list here. The measure of angle A, angle D, angle B, angle E, angle C, and angle F. They're grouped that way on purpose because A and D are on that light line, and BE are on that light line, and CF are on that light line. When you have a small triangle like this, sometimes in order to accurately use a larger protractor, we need to draw auxiliary lines that go off to the side. So I'm going to draw this line. In fact, I know in the future, well, I'll do it later in the future when I get there. I have a line. I'm going to keep drawing it out that way. So starting at A and drawing it way out through C. And then I'm going to line up AB, and I'm going to draw a long angle arrow going from A way past B. And I can now use my protractor to measure the span of the angle between these two rays. So the center of the protractor will go on A. If my protractor is twisted or tilted a little bit, there is a method to just leave it the way that it is and calculate the angle, but it's just kind of good practice to twist the protractor level. So now that it's level like this, I have 0 on my extended line AC. I should say ray. It's a ray, extended ray AC. And then I look out here and I see that I'm at about approximately 32 degrees. Right? It's not 152 degrees. There are 2 numbers at every location on the protractor. And because this is a small angle right here, even though it stretches out much bigger than the shape, it's still a small angle, small acute 90 degrees or less than 90 specifically. Because that's the case, it is going to be the small number on the protractor. I'm specifically picking 32. I'm going to do the same thing for from D, I mean. I want to compare D measurement to A measurement. So I'm drawing DF longer. Then I'm going to go up here. I'm going to draw DE longer. And then I'm going to use the whole of the protractor. I'm going to try to be as close to exactly the middle of the protractor as possible. Notice this right here. There's some words and some writing under it, but if this is 30, that's 31, and that's 32. So the measure of angle D is also, no surprise I hope, also 32 degrees. Then let's keep going. Let's figure out the measure of angle B and doing the exact same thing as I did for A and D. So if you don't mind, I'm going to go ahead and pause my talking, but keep on working. You should work as well. Use your protractor to measure the other 4 angles, and let's compare our numbers in about 40 seconds, okay? Otherwise, skip forward, pause, and then do your own work to catch up to mine, and we'll just compare our notes, all right? Here goes. Okay, I'm going to draw a little longer. Yep. And then draw BC a little bit longer. And then measure the angle, so I'm lined up. And it looks like it's about 96 degrees. Okay. So then we're going to do the same thing. We're going to extend E a little longer, going this way. We're going to extend EF, going this way. We're going to line up our protractor, line up the 0, and then this is 90. Yeah, it's 96. It should be 96 as well. 96. Okay. And then last of all, so many lines, but that's all right. So now we have a C, and we have FD, which draw it all the way to the edge of the paper. We have EF, draw that all the way out to the edge of the paper, and we have BC all the way out to the edge. Not quite. Far out though. Yeah, about like that. Okay, so we're angle C. Angle C, center of the protractor, line up the 0. Then I have about 52. Yeah, 52. Okay, and same thing for measure of angle F. So center of the protractor, 0. Line it up, get it in the middle, 52 as well. Okay, so we're back, right? Surprise, surprise. If you followed along, you can notice that the pre-image to the image will preserve the size of the angle. That's what we mean by shape. I guess that's the key thing. Shape is preserved in the angles on the image. Size, well, one's clearly smaller than the other, but the pre-image angle compared with its image angle are going to be the exact same amount. We need to write a what can you conclude? I guess I said it, but I'm going to see if I can get the sentence that, probably is the most directed best one. The corresponding angles are congruent because the measures of the corresponding angles are the same. Corresponding angles is one of our vocab words when we were talking about parallel lines, and there are parallel lines all over this thing when you start to extend. So corresponding angles are created specifically like this angle A and this angle D. They are corresponding angles. They go in the same direction. So the corresponding angles have the same measure. Therefore, they are congruent. I'm going to write that, and then I'm going to say thank you for the video. So here we go, writing it out. .448 is next. Thank you for watching. See you in the next video.